Chapter 3, Section 2, Equations for Kinematics in Two Dimensions. So the important thing in this section and this chapter is that everything is going to be broken up into its x and y components. Because now we're dealing with kinematics in two dimensions. Before, in Chapter 2, we were dealing with kinematics in one dimension, so we wouldn't have to take into account things moving at an angle. Things are just moving in a straight line. Also, trigonometry is going to be very important because we're going to have to be able to use the sine, cosine, and tangent functions to solve for unknown variables. But we'll see this when we start solving for problems. So what we mean when things are broken up into its x and y components is essentially all your kinematic variables in your x and in your y. So you would have a final velocity in the x and a final velocity in the y, an initial velocity in the x and an initial velocity in the y. But the important thing to know here is that time is always going to be the same. Time has no x or y component. So your time in the x is going to be your time in the y. So when they give you a problem and they tell you that something takes like 42 seconds to go maybe 3 miles, when you're breaking up into x and y components, your time would always be the same. Also, in the bottom, you can see how the variables are applied to the kinematic equations, basically the same way you would do for any regular kinematic equation in one dimension. Okay, so check your understanding. The problem says a powerboat starting from rest maintains a constant acceleration. After a certain time t, its displacement and velocity are r and v. At time 2t, what would be its displacement and velocity, assuming the acceleration remains the same? So we know our initial velocity is 0 because it's saying starting from rest, and its acceleration is constant. And they also give us the variables for our displacement and for our velocity, which are r and v. So there are two ways to solve these type of problems when it's asking you for the change in a certain variable. You could either plug in numbers and values into your variables to see how they would change according to what they ask you, or you could derive equations. For AP Physics, it would be better to learn early how to derive equations because sometimes plugging in numbers can take a longer time and they could be harder sometimes. So we're going to do the deriving method. So we're going to start off with displacement. So they give us our initial velocity, our acceleration, and they give us our displacement. So we're going to use the equation that our displacement equals to our initial velocity times our time plus 1/2 of our acceleration times our time squared. So that's basically just simplified into our displacement equals 1/2 of our acceleration times our time squared. So the important thing to know here is that acceleration is constant. So no matter what happens to any other variables in the equation, your acceleration is always going to be the same. Acceleration is going to be the same in the beginning, and acceleration is going to be the same in the end. So we're going to use that fact to be able to derive an equation to see how the problem would change when our time is changed. So since our acceleration is the same, we could say that our acceleration is equal to 2 times our displacement divided by our time. So that's basically our acceleration in terms of our displacement and time. So since they're asking us what would happen to the displacement and velocity if the time were doubled, we would use this equation to plug in that information. So we would do 2 times t squared, which is 4 times t squared, and in order for our acceleration to be the same, we would have to multiply displacement by 4. So 2 times 4 times our displacement squared over 4 times t squared would equal to the same acceleration. So it's basically 4 times our displacement is equal to 1/2 of our acceleration times 2 times our time squared. And in solving for our velocity, we would do the same thing, except we would use a different equation. We use that our final velocity equals to our initial velocity plus our acceleration times our time. So our velocity equals to our acceleration times time, because our initial velocity is 0. Therefore, we would get a we would get a in terms of v and t to give us a equals vt. So in order for our acceleration to be the same, when our time is doubled, our velocity has to double too. So 2 times our velocity equals to our acceleration times 2 times t. Which makes sense. If our acceleration is applied for twice as long, it's going to produce twice as much velocity if you're starting from 0. Therefore, our answer would be C. 4r and 2v, or 4 times our displacement and 2 times our velocity. Again, sometimes plugging in numbers could be simpler. I think maybe this one it would have been simpler just to plug in numbers, but again, learning how to derive equations is very helpful in the future. And it's better to start early than struggle later on. Okay, so this problem says in figure 3.5, which is a little figure here, the directions to the right and upward are the positive directions. In the x direction, the spacecraft has an initial velocity component of v initial in the x equals to 22 meters per second and an acceleration component of 24 meters per second. So we write down our variables. Our initial velocity in the x is 22 meters per second, and our acceleration in the x is 24 meters per second squared. It tells us in the y direction, the analogous quantities are v initial in the y is positive 14 meters per second, and acceleration in the y is 12 meters per second. Remembering that time is going to be the same for both our x and y components, it gives us a time of 7 seconds, so time in the x and time in the y is 7. And it's asking us to find the x and y components of the spacecraft's displacement. So it's asking for our x and our y. So we would start off by finding the equation that we could best use here. So that would be that our x is equal to our initial velocity times our time plus 1/2 of our acceleration times our time squared. So since we have the same variables for both our x and y, we can use the same equation for solving for our x and y components of displacement. So x equals to 22 times 7 plus 1/2 of 24 times 7 squared, which is just plugging in the values for the x, equals to 742 meters. Then we do the same thing for y, and we get that 14 times 7 plus 1/2 of 12 times 7 squared equals to 392 meters. And that's basically how you would solve for the displacement. It's essentially the same thing as in chapter 2 when you were doing for one-dimensional kinematics, except here they give you 2 sets of variables for our x and our y, and asking you for 2 separate components, our x and our y. Okay, so this problem says a spacecraft is traveling with a velocity of v initial in the x equals to 5480 meters per second along the positive x direction. The 2 engines are turned on for a time of 842 seconds. One engine gives the spacecraft an acceleration in the positive x direction of 1.2 meters per second squared, while the other gives it an acceleration in the positive y direction of 8.4 meters per second squared. At the end of firing, find the final velocity in the x and the final velocity in the y. So we start off by writing our variables. V initial in the x is 5,480 meters per second. Our time is 842 seconds. Our acceleration in the x is 1.2 meters per second squared. Same thing for our acceleration in the y, it's 8.40 meters per second. Our time is 842 seconds. And since they're telling us that it's moving in the x direction, along the x direction, we would assume that there is no velocity in the y, because it's telling us that the spacecraft is traveling with a velocity initial of 5,480 meters per second along the positive x direction. So it would have no initial y direction, or y velocity, or it would be 0. So our initial velocity in the y is 0 meters per second. And they're asking for our final velocities in the x and our final velocities in the y. So we would start off by writing our equation, or the equation that we would use. We also have the same variables for both, so we could use the same equation for both. So we would start off by plugging in for our final velocity in the x. So we get 5,480, which is our initial velocity, plus 1.2 times 842 equals to 6,490.4 meters per second. So that would be our final velocity in the x. And then we do the same thing for our final velocity in the y. We would get final velocity in the y equals to 0 plus 8.4, 0 times 842 equals to 7,072.8 meters per second. So it's essentially the same thing as the last question. We would just finding out the acceleration in the x and the acceleration in the y for a certain problem.